Experimental study of non-autoclaved concrete prepared by Bagasse. Abstract. The main focus of this research is on the creation of concrete utilizing Bagasse as a partial replacement for cement in non-autoclaved concrete. The building's dead load also includes a load of partition walls and ordinary mortars. Bagasse has a low density, which helps concrete to be lighter. With the addition of Bagasse, compressive strength increases by 10% and split tensile strength increases by 10.5%. It also reduces the price of concrete by 12%. The prepared concrete has a 20% higher water absorption rate but is 5% less dense. Keywords: aluminium powder, non-autoclaved concrete, Bagasse. 1. Introduction. The primary structural material used in non-autoclaved concrete is used for various structure components, both auxiliary and non-basic, as well as building components. Concrete has several advantages, including its ease of installation, high compressive strength, customizable quality, and local availability. In any case, concrete has a weight limitation as well. When applied to tremor-prone regions like Indonesia, this is a significant burden. Frothed concrete is an alternative structure material used to reduce the risk of building damage caused by a seismic tremor disaster. Since the beginning of the 20th century, non-autoclaved circulated air through cement, AAC, has been mechanically delivered as a structural material. It is a cement obtained by consistently dispersed, closed air bubbles. Because AAC has 1/6 to 1/3 the thickness of traditional cement and a similar proportion of compressive quality, it is useful for cladding and infills, as well as for bearing divider segments of low to medium ascent structures. Furthermore, because its warm conductivity is 1/6 or less than that of solid, it can provide cost-effective structure solutions when used in low-vitality structures. The material has incredible fire-rating properties, and its fire resistance lasts slightly longer than traditional cement of a similar thickness. It is not susceptible to form development, and due to its inner porosity, it has an extremely low solid transmission and is acoustically extremely powerful for a material of its weight. To control the thickness of the solid, frothed concrete is created by presenting air through the exclusive froth procedure. The thickness of frothed solid ranges from 300 to 1,800 kg per cubic meter, which is significantly less than the thickness of ordinary cement, 2,400 kg per cubic meter. Invulnerable to disappointment as a result of bacterial, creepy-crawly, and fire harms. Cell concrete, also known as circulated air through cement or froth concrete, is made of concrete, lime, silica sand, and occasionally pozzolanic material, in which air voids are entangled in the mortar lattice by methods for a reasonable frothing specialist. It is classified into 3 groups based on the pore development strategy: air entraining technique, gas concrete, utilizing compound response in glue for gas creation, frothing technique, frothed concrete, bringing air into the glue with the addition of bubble stabilizer, and combined strategy, bringing air into the glue utilizing concoction response and balancing out it with gas stabilizer. Because of the relieving temperature, cell cement can be divided into 2 groups, one that is restored at nearby or marginally raised temperatures, and the other includes precast brickwork items that are not autoclaved at a temperature fundamentally higher than 100 C in a pressurized and steam-warmed condition. Because of intentionally entrained air and a lack of compaction, the pore framework in concrete-based material is routinely delegated gel pores, slender pores, and macropores. In comparison to gel pores, fine pores, and other large pores are prone to quality decline. Examination techniques such as nitrogen gas assimilation, mercury porosimetry, optical microscopy with image handling, and X-beam registered tomography with image preparation can be used to identify the type of pores. The pore arrangement of autoclaved circulated air through cement is classified as I-fake air pores, intercluster and interparticle pores, 2, macropores formed by mass development caused by air circulation and micropores that appear in the dividers between the macropores, and 3, smaller scale vessels, 50 nanometers to 50 lm, and fake air pores, greater than 50 lm. Circulated air through cement is typically made up of lime, concrete, gypsum, and sand, or pozzolanic materials, with traces of aluminium powder added as a pore shaping specialist. The aluminium reacts with lime, which releases hydrogen gas and forms a large number of small air pockets that are constantly conveyed in the framework 9,10. After the set, the circulated air through cement was cut into precise dimensional units and then restored in an autoclave with a best fixed pressure of 1.0 to 1.2 MPa for 5 to 8 hours. In contrast to the traditional autoclaved circulated air through cement, AAC, non-autoclaved circulated air through cement, NAAC, has a significant amount of leeway in encouraging the assembling procedure and decreasing the cost of items. During the NAAC development, steam restoring was directed at temperatures lower than 100 C for 8 to 24 hours after being cut. As a result, when compared to AAC, the NAAC has the element of security in the item process with low vitality utilization. AAC is manufactured and displayed as a brickwork unit in the majority of global markets. It is frequently used to replace various types of stonework material, but because the material is solid yet, it is frequently used in a thickness that is significantly greater than for other materials. AAC can also be used to make delicately fortified story stature components or more intensely fortified components for floorboards, rooftop boards, divider boards, lintels, pillars, and other exceptional shapes. These components have a wide range of applications, including private, commercial, and modern development. Stronger divider boards can be used as cladding frameworks, as well as load-bearing and non-load-bearing outside and inside divider frameworks. Fortified floor and rooftop boards can be used to provide a flat stomach framework while supporting significant gravity loads. One of the key properties of AAC fabrication is the process's adaptability in terms of item attributes and item sizes. As a result, there are numerous different organizations in which the items could be manufactured. 2. Methodology. For the investigation of non-autoclaved concrete, the different extents of sand and concrete with water concrete proportion of 0.50 is taken for the contemplations. What's more, results are inferred based on compressive strength, split elasticity, water assimilation, and cost per cubic meter. Subsequent to choosing the legitimate proportion, the blend was tried with the water concrete proportion of 0.40, 0.45, 0.55 and 0.60. Since lightweight substantial necessities more water to respond with alumina powder to start the response of the air circulation measure. For non-autoclaved circulated air through concrete, the planned blend amounts ought to be decreased to 60%, and the measurements of alumina powder is to be tried. The dose of alumina powder is 0.1%, 0.2%, 0.3% and 0.4%. Alumina powder on response with water produces air which assists with creating circulated air through substantial when blended in with water. So the diverse expansion of alumina are tried. As per the experimental study, the bagasse ash to be introduced in the composite mix, hence it contains pozzolanic properties. It will be helpful in reducing environment waste and emission of CO2 from the concrete. 3 results. Figure 1 dry mix of non-autoclaved concrete. 2.1 normal proportions of cement and sand. In the trial investigation of different proportions, 1:3 is observed to be exceptionally viable as far as strength, cost, thickness, and water ingestion. The proportion 1:1, 1:2, and 2:3 have higher concrete substance, which has 2 issues. First is hotness of hydration. As higher the concrete substance, higher will be the fieriness of hydration. Second, economy. Higher concrete substance is anything but a financial agreeable. As the concrete substance expands, the thickness of substantial increments. As the concrete substance expands, the pores in the substantial fills, which increment the strength of cement yet diminishes the water ingestion. Examination shows that at W/C proportion 0.50 gives ideal outcomes as far as strength. As the water content in substantial builds, the water request insignificantly changes because of less development of hotness of hydration, and concrete glue with additional water fills the pores in the substantial, so it likewise ingest less water, implies changing the water content doesn't influence the water retention of cement. In any case, the water content makes an irrelevant impact on the thickness of cement. Alumina powder on reaction with water forms air bubbles which creates pores in the concrete, so different proportions are tried to check the exact dosage of the alumina powder for the formation of lightweight concrete. With replacement of cement by bagasse ash in proposed aerated concrete. Mix. Ratio of. Proportion. Compression. Split tensile. Water. Cost, excluding. Density. Expansion in bagasse debris content increment the strength boundaries because of its pozzolanic activities, yet it additionally expands water ingestion limit of cement since bagasse debris is water restricting debris and it effectively retains water. Utilization of bagasse debris can diminish the thickness of cement, for example decrease in weight, and utilization of bagasse debris can be result into the decrease in cost too. Density of lightweight concrete in kg/m3. Water absorption in kg/m3. Different lightweight ratios with different bagasse ash content. Water absorption and density chart of different bagasse ash content. Water absorption. 4. Conclusion. 1. Bagasse debris can be effectively supplanting concrete up to 20% because of its pozzolanic activity. 2. For the specific proportion, bagasse debris can decrease the expense of lightweight concrete up to 12%. 3. Bagasse debris additionally decreases the heaviness of cement up to 6%. 4. Increase in the strength because of bagasse debris can be seen up to 30%. 5. Due to utilization of bagasse debris, water ingestion of substantial increments up to 18%.